Good morning, engineers. It's Mr. Heller with another piece of work and the last piece of work for this half term. So today we're going to be looking at some ideas about friction. So I've got some relevant formulas from the formula sheet here. We've got acceleration due to gravity, saw that last week before that as well. Got a general formula for force. Force equals mass times acceleration. This is the new one here. Force to overcome limiting friction, F equals mu n, this kind of U shape. It's a Greek letter M, and it stands for the coefficient of friction in this case. And then N is the normal reaction or the normal force on an object. Okay, so let's just pick this apart a little bit. The frictional force, the force needed to overcome friction, so something that's a force just to get something started moving, or when something's moving and there's friction applying on it, then we're going to have some frictional force, and that's going to be a relationship between mu, coefficient of friction. Now that's just a number, it's a dimensionless number. It could be really small if the contact between two surfaces is really slippy. It could be really big if there's a lot of grip going on there. We're not talking about adhesion here, some things that are sticking to each other, but gripping in a frictional way. And this N, this normal force, is worth a little bit of talking about as well. So whenever an object is in contact with a surface, then we can have a normal force that acts at right angles between that contact, and that's this meaning of the word normal, means at right angles to. So if an object is sitting here with a weight, and it isn't moving through the floor, then there's going to be a balancing force that we call the normal reaction force. Okay, so in A-level maths, this is sometimes called R. In this formula booklet, it's called N for normal reaction. Okay, and it's important to realize that this is a function of two things being in contact with each other and exists even if we don't have any friction. Okay, so now we've done that, we could say, okay, we've got mu, that's a function of the slippiness between the two surfaces that are in contact with each other. So if two things are really tightly gripping each other, then we're going to have a lot of friction if that's a big number. If they're really slipping over each other, then we're going to have a little bit of friction. And it's also going to have a lot of friction if we've got a big normal reaction force, and a little bit of friction if you've got a little bit of normal reaction force. And really, because the normal reaction is going to be equal to the weight, unless there's some other force coming in with a vertical component, we can say that the heavier something is, the more friction it's going to have. And that kind of makes sense. If you imagine trying to push a heavy object across a rough surface, we're going to have a lot of friction there. If you're trying to push a light object across the same surface, then we're going to develop less friction. Okay, so let's have a look at one of the questions. I've got two worked examples for you today. Okay, it says a force of 7 newtons is applied to the side of a 3 kilogram block that's sitting on a rough surface. The block experiences a frictional force against the force that's applied. We're going to start off by drawing a force diagram for the block. Okay, so I'm going to model the block just as a square or a rectangle. Doesn't really matter what shape it is. And I'm going to say, obviously, this block has a weight. And then because the block's not accelerating through the floor, there must be what I'm going to call a normal reaction force going upwards. If this wasn't balanced, then it would be accelerating downwards, and it's sitting on a surface. So obviously they're balanced. I've then got this force of 7 newtons that I'm going to push in the side. And then it says there's some sort of friction coming out the side here. Okay, what's the weight of the block? Well, it looks like we've got a weight of the block here, 3 kilograms, but that's a mass. Okay, I'm going to say that the weight of my block is equal to m times g. So that's 3 times 9.81 newtons, which, if I calculate that, is going to come out as 29.43 newtons. I'll not round it off yet, but obviously if that was my final answer, I'd write it down as 29.4. The normal force on the block, because the forces up are going to equal the forces going down, I can just say that the normal force on the block is going to be exactly the same as the weight of the block, not the mass, because we're talking about forces here. Okay, the coefficient of friction is 0.15. What's the force needed to overcome friction? Well, remember that formula from my previous page, F equals mu times N. And I'm told that mu is 0.15 in the question. Got it there. And I'm going to times that by the normal reaction force, 29.43. And because this doesn't have any units to it, it's just a number, the force on that side and the force on that side, the units are consistent there. And that's going to come out as 4.4145 newtons. And again, I could round that off to 4.41 if I wanted to. But because I'm going to work with it later on in the question, I'm not rounding it off yet. And the resultant force on the block, well, let's have a look. We know these two are balanced, and I've got 7 newtons coming in here, and I've got less friction than 7 newtons. So I'm going to say that the resultant force in a horizontal direction is 7 minus 4.145 newtons, which, if I calculate that, is going to come out as 2.5855 newtons horizontally. Okay, and then what's the acceleration of the block from the resultant force? Well, we're going to need to apply the fact that force equals mass times acceleration. And because force equals mass times acceleration, doesn't take a huge amount of rearranging to see that A is going to be the force, the resultant force, divided by the mass. My resultant force is 2.5855. When I divide that by the mass of the block from right at the top of the question, divided by 3, that's going to come out as 0.8168 ... and round that off to 0.817 meters per second squared. So quite a lot of steps in here. We started off with a force diagram to keep everything in check. We're going to say that the weight of the block is m times g. The normal reaction on the force is exactly the same as the weight, because it's the only vertical forces that can balance each other out. The coefficient of friction is related to this normal force. So I've picked that number up from there and substituted it in there. The resultant force horizontally, 7 in a positive direction, friction of 4 and a bit in a negative direction. So overall 2 and a bit. And then I've said that's my resultant force, which we can divide by the mass to find the acceleration of the block. Okay, so that's a situation where something's accelerating, where the friction doesn't quite balance out the pushing force. So this object's going to be getting faster and faster. Second question that I'm going to go at, and I'd like you to have a go at on the worksheet with the answers, is where something's moving at a constant speed. Now, where we say constant speed, this could be 0. Okay, so this block could just be sitting there, ready to start moving. Okay, it's feeling a force from the side, but it could be 0, the speed. Okay, so we're going to have a force diagram on the block again. I'm pushing this time with 30 newtons. I've got friction opposing that force. I've got weight. And I've got a normal reaction force. So the weight of the block, again, I'm going to say that the weight is always going to be mg. I know the mass is 10 times by 9.81, assuming we're on Earth, 98.1 newtons. And then again, the normal reaction, these are the only vertical forces that are acting. So the normal reaction must be 98.1 newtons, because otherwise it would be accelerating up or accelerating down. And the coefficient of friction, well, let's have a look. My formula from the previous page said F equals mu times N. A little bit of rearranging again. mu equals F over N. The force from the side, or the friction, is 30. The normal reaction is 98.1. So this gives me a coefficient of friction, if I work it out, of 0.3051 ... or 0.306 to 3 significant figures. Now this is a dimensionless quantity. I've not missed the units out. There are no units to this. Don't be thinking that that's going to be measured in newtons or anything. It's a force divided by a force, so the units are going to cancel. It's a dimensionless quantity. Then what's the work done as the block moves 3 meters? Well, the work done is equal to force times distance. Remember from that previous week's work. Okay, and the force pushing is 30 newtons times 3 meters. So that comes out, because it's work done, I'm going to express that in joules. I could call it 30 Newton meters. Newton meters is really a unit that we'd reserve for torque or for a turning force or a turning moment. So 90 joules there. So let's have a look what I've done. Started off with a diagram. Notice that this constant speed could be zero speed, could be static, could be waiting to move. The weight of the block, just mass times g. The normal reaction, up force equals down force. Coefficient of friction, well, I've kind of said the friction here is going to have to be 30, because left force equals right force if it's a constant speed or if it's static. And then the work done as the block moves 3 meters, 30 newtons times 3 meters, 90 joules. Okay, so there's a few questions very similar to these for you to have a go at on the worksheet, and an exam question for you to have a go at, which is more straightforward than these. So good luck. Don't forget to email me if you've got any problems.